Welcome to this week's Center of Math's Advanced Knowledge Problem of the Week. For this week's problem, we have a commutative ring A with an ideal J, and we want to prove that the quotient ring A, quotient J, is an integral domain if and only if J is prime, and A/J is a field if and only if J is maximal. So first, let's assume A/J is an integral domain. So if A quotient J is integral, this means if we have UV, remember A quotient J, UV equals 0, that means at least one of U or V must equal to 0. So this implies note that we say our U or V are equivalent to the canonical epimorphism, sending each element of A to its corresponding element in A quotient J. Say theta A equals U, theta B equals V. So we know one of these A or B, because this equals 0, and because this is integral, that means one of these must equal 0. And so one of these must actually be a member of J. And so J must be a prime ideal, because we must have one of these equal 0, which is equivalent to one of these being A or B being a member of our ideal. And so now we can assume that J is a prime ideal and prove that A/J has to be integral. So let's assume J is a prime ideal, and let's also assume A quotient J is not an integral domain. So we have some UV equals 0, where neither U nor V equals 0. And so saying using our epimorphism, some theta A equals U, some theta B equals V. So we have A comma B is a member of J, but neither of these are 0, so neither A nor B is a member of J. And so J cannot be a prime ideal. And so this contradicts our initial assumption that A quotient J is not integral, so it must be an integral domain. And so that finishes the first part, that A quotient J is integral if and only if J is a prime ideal. So let's first assume A quotient J is a field. So we have some U, member of A quotient J, and V, because it's a field, it has an inverse. U times V equals 1, the identity in our field. And consider the set A, B plus J, where the epimorphism, saying the coset corresponding to A is U. And so that means we have some coset corresponding to B, which corresponds to the coset V. So we have some B such that AB plus J equals 1. And so we're considering J and we append on one more element, A, non-J, and A is arbitrary. Now note, if we append A, so we want to prove J is maximal. So any ideal containing J must be the whole ring. So we append A, we look at the ideal containing A. So we have anything on the form AB plus J is again in our ideal. But AB plus J, we have some AB plus J equal to 1. So 1 is again in our ideal containing another element. And so this slightly larger ideal, let's call it M, because it contains 1, must contain every element in our ring, and so it is a whole ring. So any ideal bigger than J must be the whole ring, and so J is maximal if a quotient J is a field. So we want to take an arbitrary A, non-J, consider the set AB plus J, B is any member of A. Note that we said B equal to 1, B equal to 1, J equal to this J value to 0. So A is a member of this ideal here. And so because A is a member of our slightly bigger ideal, this is actually all of A, our initial ring. So rearranging a little bit, we have A times B equals 1 minus some J. And then using a canonical epimorphism, sending each element of A to its corresponding element in A quotient J, we have theta B equals theta AB, which equals theta 1 minus J, which is just the unit element in our quotient ring. And so saying theta A is our arbitrary element of our quotient ring A slash J called U. We have some V, also a member of our quotient ring, such that U times V equals 1. So U has an inverse, and so A quotient J, it must be a field. Thanks for watching. Please check out censormath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.